oblique collisions between particles, which we had just about started in the last lecture. Okay, now you'll see a very interesting and important special case of oblique collision. Okay. So oblique collisions of two particles or bodies. So the special case of this one, if masses are identical, okay, and a perfectly elastic collision occurs for a moving body making an impact on a stationary particle. Okay. Then let's see the important result that we'll get. So first, let's visualize this collision. So there are two bodies like this, which are of identical mass, let's say. Just a moment. Yeah. So let's say the two bodies here, A and B, are of same mass, but B is stationary initially and A is moving with a velocity V like this. Mass of A is equal to mass of B, and the collision is perfectly elastic. So what will happen in that case is that the final velocities after impact will be perpendicular to each other. Okay. So let's understand why that will happen. So let's say they come in contact somewhere over here. As they come in contact, you can see that the collision impulse that will act will be along the center to center line. So this one will experience an impulse like this. This one will experience an equal and opposite impulse like this. So if this is the collision impulse, then immediately after the impact, now what you can see is that they will move off with velocities which are in these sort of directions, which I'm going to show. So the body B was at rest initially. So its final velocity will be in the direction in which the impulse is acting. So that will be along that center to center line. So this will have a velocity VB like this. Okay. But A had an initial momentum like this, which was mv0, and it experienced an impulse like this J. So the final velocity should be like this. Sorry. The final momentum after impact should be equal to the initial momentum before impact plus the impulse. So you can see that the final momentum of A should be in this sort of direction. So in this diagram, you can see that therefore A's final velocity will be in this sort of direction. Now what this theorem is saying, that it is guaranteed that these two will be perpendicular to each other, that this VA and VB. So VA should be perpendicular to VB. Okay. This is the theorem. Okay. Now let's see why that is the case. So what is the proof of this? So first of all, we have this vector relation is coming from conservation of linear momentum. Which is a fact for all collisions. Okay. So V0 should be equal to VA plus VB because the masses are same. Okay. That's equation 1. But in addition to that, what is also happening here is that half mv0 square should be equal to half m VA square plus half m VB square, because it's a perfectly elastic collision. So there is conservation of kinetic energy. Remember, that is also a definition of perfectly elastic collision.
Yes, sir.
Because it is. So there are two ways we can define perfectly elastic. One is that kinetic energy is conserved, and the other is that separation velocity is equal to approach velocity. So here we are using the more fundamental definition that kinetic energy is conserved. So V0 square is equal to VA square plus VB square, or from that we can imply that the magnitude of V0 is square root of VA square plus VB square. So now the moment you compare equation 1 and 2, you can see the proof of why VA is perpendicular to VB, because the vector sum of two vectors VA and VB is such that the magnitude of the vector sum is square root of VA square plus VB square. That means they have to be perpendicular. This is something that you understand from vector algebra. So this shows you that the moment these two conditions are satisfied, that the masses are equal and that kinetic energy is conserved, it means that VA has to be perpendicular to VB. Okay, so from equations 1 and 2, you can see that mod of VA plus VB is equal to root of VA square plus VB square. So that means that VA is perpendicular to, or the angle between the two vectors is 90 degrees. Okay, so that's the proof of this theorem, and this is an important special case or theorem related to oblique collisions. So whenever we have this situation that the masses are equal, the collision is elastic, and a moving body comes and hits obliquely a stationary body, then they have to separate perpendicularly to each other. That means after impact, they will be moving in along lines which are mutually perpendicular. A will be going off like this, and B will be going off like this, and this is at 90 degrees to each other. If you just make a note of this, this is an important theorem. You can get direct questions based on this theorem, which to solve them, you should know this from beforehand. Okay, so hope this is clear. So let's understand an example.
Sir, I was writing.
Okay, okay. Just a moment.
Sir, your screen is blank.
Yeah, just a second. Just a moment, people. I have to reboot that software. It's Okay, so done with this now. So let's look at an example question. So we have a mass m which is moving at 10 meters per second, and it makes a perfectly elastic head-on collision with this other mass m. Okay. Sorry, not head-on, but oblique. Such that the final speed of the first body, which was moving at 10 meters per second initially, is 6 meters per second. So find the speed of the second body. Okay. And the direction in terms of angles of each one's final velocity with respect to the direction of the first body's initial velocity. So that is with respect to this line along which that 10 meters per second velocity is. What is the direction of each one? Just try this out, this question. Okay, anybody got the answer?
Sir, still weak.
Okay, so let's work this out quickly.
Sir, 8 meter per second.
Very good. So one, though, we can understand directly from the theorem that if this is the situation before impact and this is the situation after impact, you can see that this angle will be 90 degrees, which means that with respect to this direction, if this makes some angle theta, then this will make an angle of 90 minus theta. That also will be. So we have, okay. So the first body is moving at 6. So the second one, we can see its speed will become 8 meters per second. we're talking about speed, so we won't write plus minus, we'll just write this. Okay. Now we'll also see that for theta, anybody found this value of theta? So I'll just give you a hint. You know that if this angle is theta, then the other one is making angle 90 minus theta. So you just take this as your x-axis and take this as your y-axis and apply conservation of momentum. So when you apply this along y-axis, you get that 0 is equal to mv1 sine theta minus mv2 sine of 90 minus theta. So we get p1 sine theta is equal to v2 cos theta. Now from here v1 was how much? It was 6 and v2 we just saw is 8. So you can see tan theta is 4/3, which means theta is 53 degrees. So that means the first body is at theta equal to 53 degrees and second body at 37 degrees with respect to that velocity. Okay, now let's see another version of this kind of application. So in the above question, we saw that directly we were given some information about the speed of the first one after impact. Now there can be a situation where we are not given direct information like that. Rather, the information is a little bit indirect like this, like some geometrical term is given to us. So I'll explain how that works. Okay, so suppose we are given this information here, which I'm showing. This distance is called d. Okay, so d is equal to the perpendicular distance of the line of action of A's initial velocity v0 with respect to B's center. V naught, which is A's initial velocity, with respect to B's center. So this quantity D, it is called the impact parameter. So basically you can also understand that if impact parameter is equal to 0, then that would be the case of a perfectly head-on collision. Okay, D equal to 0, this implies head-on impact. Whereas if, for example, D is greater than the sum of their radii, this radius here is Ra. And this radius is Rb. So if D happens to be greater than this, then as you can see, if D is greater than the sum of the two radius, then there is no impact. They miss each other. Okay. But in the case where D is greater than 0, but less than R1 plus R2, in this case, there is an oblique impact. Okay, so that is the significance of this term, impact parameter, in an oblique collision. Here you can see that this distance D is less than the sum of Ra plus Rb. Okay. Because Ra would be this distance here, and Rb would be this distance here. So you can see that this is less than the sum of Ra plus Rb. So there is an oblique impact as long as D is greater than 0 but less than the sum of these. So that is the case that we are considering over here first. So first of all, this is the term called impact parameter. Okay. Now coming back to the question, so it is given that A and B are identical disks of mass m each and radius r each. Okay. Now, if this impact parameter D is equal to, let us say, the impact parameter is 1.6 times r. So it is, you can see that this is that case where D is greater than 0 but less than 2r. So it is an oblique impact. So in this case, we have to find final velocities B and BB for perfectly elastic collision. Okay. For a collision with E equal to 0.5. So these two different cases, we have to find the velocities. So try out the first part, you should be able to understand it geometrically. So the hint to you is just draw the two spheres or the two disks when they come in contact and use the value of impact parameter to find out what is the angle at which the impulse acts on B. Because remember, B's direction of motion after impact will be along the impulse because B is at rest initially. So from that, you will get B's direction of velocity. And you will use the theorem that if it is perfectly elastic, then A's velocity should be perpendicular to it. So from that, you can figure out the direction in which A is moving. And once you got those directions, you can just apply momentum conservation and find out their final velocities. So in this case, you will get the final velocities in terms of V naught. Okay, because I've not given the value of V naught. So just get them as some factor into V naught, and you'll get the angles at which they are happening. So just try this out, people. Okay, so just got the answer from a couple of people. So anyhow, see, the thing is you have to work out the angle from the geometry. So this is what I meant when I said that try and work out the angle from the geometry. See, these are the two discs when they come in contact. Now the initial velocity of the first one if that was along this line, and the impact parameter is the distance of this line perpendicularly from the center of the second one. So that means if I draw the center to center line, this is, let's say, the center of the second one B. So if I draw this center to center line, and if I drop this perpendicular here, so this one is D in distance, and this center to center line is 2R. So you can see what this angle is. If this angle is theta, you can see that sine theta is equal to D divided by 2R. Now remember, D was given to us as 1.6R, correct? 1.6R? Yeah, 1.6R. So you can see that theta is sine inverse of 0.8 or sine inverse of 4 by 5. So that means theta is how much? Theta is 53 degrees. Now when they come in contact, the collision impulse will be along this line, along the center to center line. So the impulse acting on A will be like this, and the equal and opposite impulse acting on B will be like this. And the masses are equal. So in the first case, if we take that the collision is perfectly elastic, we know that the final velocities will be perpendicular to each other. Okay. So B will have the velocity along this center to center line, and that velocity is, let's say, VB, and E will have the velocity perpendicular to it, so that's along this line. And compared to this, the direction of V0, that is like this, where this angle is 53 degrees. So this angle will be 37 degrees. Okay, so this is the first case where the collision is perfectly elastic. So VA is perpendicular to VB after impact. Okay, so we have VA sine 37 is equal to VB sine 53. This is coming from conservation of momentum. Applied to this system. So taking this direction as our x-axis and this direction as our y-axis. You apply conservation of momentum along the y-axis now to get this equation. Okay, so we get this equation. So this tells us that 3VA is equal to 4VB. Okay, and if you apply conservation of linear momentum along x-axis, you have the equation that MVA cos 37 plus MVB cos 53 degrees is equal to mv1. So we have 4 by 5 VA plus 3 by 5 VB is equal to V0. This is our second equation. So now solving equation 1 and 2, we can find the answers. So these are the final speeds for the case where the collision is perfectly elastic. Okay, so hope you have understood this case. Now let's come to the situation where the collision has a given coefficient of restitution. Okay. So how to interpret the coefficient of restitution in this case? So basically separation velocity is equal to 0.5 times approach velocity. Now if you look at the situation just before impact, you will realize that the approach velocity will be the component of, so this is just before impact. In the diagram it looks like they've come in contact, but this is just before they come in contact. So at that instant, you can see that the velocity of A is along this direction, and the center to center line is making an angle theta with respect to it, whereas B is at rest. So the approach velocity will be equal to V naught cos theta. That is the component of A's velocity pointing towards B's center. Okay. Or along what we call the line of impact. This line over here, which I'm extending, that is the line of impact, because that is the line along with the impulse acts. So you can also think of the approach velocity as the component of relative velocity along the line of impact. That's another way in which we can interpret the concept of approach velocity. So in this particular case, we had seen that theta being sine inverse of the impact parameter divided by twice the radius was 53 degrees. So we have approach velocity equal to V naught cos 53 or 3 by 5. Okay. Now next what we'll do is we will consider that line of impact as our x-axis, and we will apply the vector relationship so just after impact. If you look at the velocities, now we'll take the line of impact as our x-axis and perpendicular to that as our y-axis. So x-axis is the line of impact. So B's velocity just after impact should be along this direction, because the impulse is acting along that direction. Okay. But A's velocity, let's assume, is in some direction like this. Okay, so it's making some kind of an angle. So you can see that A's velocity can be divided into two components. One is along the x-axis and one is along the y-axis. So now in this diagram, we can see that for velocities VA and VB just after impact. Separation velocity will become PB minus VA's X component. And E equal to 0.5 means that separation velocity is equal to 0.5 times approach velocity. So from these equations now we will see that PB minus VA's X component should be equal to half of 0.5 times approach velocity, which we have seen above, is 3/5 v0. So that becomes our first equation. Okay. And then we have conservation of momentum, which will apply. Okay. So this momentum be equal to the initial momentum, which was like this. So when we write this in this component form now, you can see that this is mvax I cap plus mvay j cap plus mvb I cap. This should be equal to mv0. Now v0, if we divide above into components in this diagram, you can see v0's components. We have taken this as our x-axis and this as our y-axis. So where theta was 53 degrees. So comparing both sides of the equation, I'll get now two equations here. On the other side, this is V0 cos theta. So cos 53 is 3/5. Plus V0 sin theta, sin 53 is 4/5. So this vector equation, when I compare both the sides, I get two scalar equations from the components. So this is like my third equation or second equation, let's say. And my third equation will become comparing the y components, which will directly give me VAY. So my unknowns now are VAX, VAY, and VB. So three unknowns, and I've got three equations. So all I need is to solve them now. So from equation 1 and 2, next thing you can see, we have this. Okay. And from equation 3, directly we have this. Okay, so we can see that VA is coming from the components Okay, so this becomes the final solution. So first of all, make sure you understand the interpretation of separation and approach velocity. So how from this diagram we are getting the approach velocity, and from the second diagram we are getting the separation velocity. Whole concept of line of impact. Okay, so these are typical examples of oblique collisions and how we can interpret coefficient of restitution in an oblique collision. The approach and separation velocity are nothing but the components of the relative velocity along the center to center line in this kind of a situation.
Done, sir.
Okay, finish with this one. Okay, so let's conclude this with an example question. Imagine we have this kind of situation. It's like three identical discs or three carom coins for that matter on a carom board table. Now, two of them are at rest and in contact like that, and the third one is going to collide with its initial velocity vector exactly along this common tangent. So A, B, and C are identical discs on a smooth horizontal surface. B and C are at rest in contact. Whereas A's velocity is along the common tangent at the point of contact. Of B and C. Okay. Now it is observed that what happens is that A comes to rest immediately after impact. Okay, A comes to rest just after impact. So find the velocities of B and C. Okay. So again, hint to use, you have to understand what happens when they come in contact. What are the line of actions or the line of impact? So A will simultaneously make impact with B and C because of the geometry. And as A makes impact with B and C, simultaneously there'll be a collision impulse acting on B and C along the center to center lines. Okay. So if you draw the center to center lines when they come in contact, you get a symmetrical figure which will give you an idea about the angles involved. And then you can just apply momentum conservation and also the given fact that A comes to rest immediately after contact. So you have to just find two velocities for which two equations will be enough. So just writing the vector momentum conservation will give you two component equations, which should be enough to solve this. So just try this out, people. Okay, so let's understand how this works. So first of all, roughly speaking, if this is like the diagram, when three of them come in contact, then you'll see that the center to center lines form an equilateral triangle. So that means the impulse that acts on this, the impulse that acts on this, and by symmetry, equal and opposite impulse like this will act on this. Okay, so they will be at these sort of angles. So that means just after impact, if we look at the velocities, this and this will have the same magnitude of velocity, but along directions which are at 30 degrees with respect to the initial velocity of the first one. So that's it. We have only one unknown. We have to just apply momentum conservation. So we can see that 2 mv cos 30 should be equal to mv naught, conservation of momentum. Because we know that A stops after the impact and B and C have some velocities like this. So very simply, we can see that V will become V naught by root 3. And once you've got this V equal to V naught by root 3, we can also calculate the coefficient of restitution for each of the impacts. So you can see that, for example, as A and B are coming in contact, or similarly A and C are coming in contact, A's velocity has
along x-axis, no?
Sorry,
So
y-axis के along to 0 है ना momentum. So
Yes.
मतलब ये vector algebra से ही ऐसा आ जाएगा ना, because you can see the initial momentum was along this direction and these two were at rest. So when we equate this mv naught vector with the sum of va plus vb, but we have got the condition that magnitude of va is equal to magnitude of vb equal to v, and the angle between them is 60 degrees. Okay, this total angle, it will give us this only. Understood, no?
Yes, sir.
Okay. Now you can see here that the approach velocity, for example, of A towards B is going to be, this angle is again 30. It's half of the total angle. So it's going to be equal to V naught cos 30. So that is root 3 by 2. Okay. And the separation velocity nothing but this speed that B directly has away from A's center is directly along the center to center line. So the separation velocity of B with respect to A is going to be V, which we just saw is V naught by root 3. So from this and this, now we can see that the coefficient of restitution, which is this ratio, will become 2 by 3. E is equal to 2 by 3. Now, instead of B and A, we have done the calculation for A and C also, would have been the same thing. So both the collisions which are happening simultaneously, the collision between A and B, and then again the collision between B and C, they are happening with the same coefficient of restitution, which is equal to 2 by 3. That is why A is coming to rest and B and C are having these symmetrical velocities at 30 degrees each and of same magnitude V naught by root 3. Okay. So this is another example where the concept is the important thing, but the application, once you convert it into numbers, is very simple because it's just a single momentum conservation equation with so much symmetry in it. So these are again typical type of questions at the JEE level for oblique collisions. Okay, people, so hope this question was clear to all of you. Okay, so with that, we conclude today's lecture and we have finished collisions. Okay, so just few things remaining in system of particles chapter, like variable mass system and applications. But mostly in the next lecture, we'll be discussing more example questions with an idea of doing some practice and doubt solving and all that. And of course, we'll take about 40 to 45 minutes to cover that part of the variable mass systems and the equations for variable mass systems like rocket systems, etc. Okay. So with that, we'll conclude the topic of system of particles, and next topic we'll do after that will be rotational mechanics or rigid body mechanics. Okay. That's it for today's session. People, wish you all the best.
Thank you, sir. Bye, sir.
Okay, bye people.